Hello, for this problem, we've got a cart with a total weight of 200 pounds, including its load. We've got two wheels, each with a diameter of 2 feet, each supporting half of this, so the weight's distributed evenly. We've got a bearing attached to each wheel. That's what's connecting the wheel to the cart itself. And each of those bearings is a lubricated steel-on-steel journal bearing. Coefficient of friction is 0.05. And we've got a 1-inch shaft diameter in that bearing. We want to figure out two things. Number one, what is the moment due to friction from each bearing? So we're going to figure out that frictional loss there. And then, assuming we have no other sources of friction, we want to figure out what's the magnitude of this pulling force such that we keep the cart moving at a constant speed. Alright, so using our journal bearing equations, the moment due to friction is going to be equal to the radius of the shaft times mu k, my kinetic coefficient of friction, times the normal force. Alright, so for this, let's start plugging in numbers. The radius of my shaft, I've got a 1-inch diameter shaft, so the radius of my shaft is going to be 0.5 inches here. Mu k was given to us, that is 0.05, that's my kinetic coefficient of friction. And the normal force on each one of these is going to be 100 pounds, because I've got 100 pounds of weight on each side, or each wheel. Alright, so if I calculate all of this out, the moment due to friction should be equal to 2.5 inch-pounds of torque. And this is for each wheel. Alright, so that is the frictional loss from each wheel. The next part of the problem, I need to figure out this pulling force right here, needed to keep it moving at a constant speed. Alright, so for that, let's draw out a free body diagram of the wheel. Alright, so for our wheel, we're going to have a few things going. So we've got 100 pounds of weight from the cart itself, and that is, we're assuming the wheel itself does not have an additional weight. We've got the frictional loss, and so if the cart's moving forward, the wheel would be rotating this way, so it means the frictional force is going the other way. It's fighting that rotation. And again, that was my frictional loss. I'm going to have that pulling force. So the pulling force is going to get kind of transferred through the cart, through the axle, acting on the center here. And since I've got two wheels, I'm going to call this 1/2 of the pulling force. And that is going to be what we're solving for in this case. Alright, so I've also got, in the point of contact between the ground and the wheel, I've got a normal force, Fn, and I've got a frictional force that's going to be causing this wheel to rotate. And so the frictional force will be going this way, causing the wheel to rotate in the direction it's rolling. Alright, so this whole thing has got a 2-foot diameter. Alright, so really what I'm looking for is this pulling force. And I can use my equilibrium equations in an intelligent way. I'm going to first do the sum of moments about what I'm going to call point O here in the center. And around that point, I've got two moments, or a force that's exerting a moment and a moment itself. So the moment is 2.5 inch-pounds, and that's going to be a positive moment using my right-hand rule. the friction force is going to cause a negative moment. So it's negative FF times 12 inches. And the sum of moments must be equal to 0. This is moving at a constant rate, so it's still in equilibrium. So FF is going to be equal to 0.208 pounds, roughly. Alright, so sum of forces in the x direction now. I've only got two forces in the x direction. I've got this 1/2 of the pulling force and this frictional force over here. So it's positive 1/2 F pull minus FF equals 0. And so my pulling force has to be equal to 0.416 pounds. And so just under half a pound of force is what's necessary to kind of keep this cart going at a constant rate. That's assuming, again, that there's no other frictional losses other than the losses we have in that bearing right there. Alright, so that's all I have for this video. Thank you for watching, and I hope to see you again.